Hi there, my name is Harry Hu. This is Physics 2211, Lab 3, Black Hole. So in our lab instructions, we were asked to do two things. So the first thing was to estimate the mass of the black hole, and then afterwards find the initial velocities that we need to not crash into the black hole. And I actually did both instructions in one part of the code, so I did it together, which it will explain why there's only one starter code that I used. So some basic introduction concepts. So obviously we have the three Newton's laws, but just relating to this one, the second law is the most important. And some things to keep note is that the net force on a star is only black hole. The force, the black hole is at the origin, is not moving, and the trajectory of the star is defined by our Georgia Tech email. So some formulas and equations and data to keep track of. So you can see the formulas listed above, and some data would be the given star mass and delta t value, and the black hole mass is what we're trying to find. And for the delta t value, we went from days to seconds. And here you can see how I changed the seed into my Georgia Tech email. So here is other given values that we define. Here again, delta t. This is in terms of seconds converted from days. And the mass is just in kilograms of the star. So for GlowScript program, so initially we were asked to find the initial final velocity. So you can see that at the top. And then using the initial final velocity, we find our momentum, which is mass times volume. And we find the rate of change in momentum, which would be final velocity minus initial velocity over time. And then we find the different force vectors, including the parallel and perpendicular, which you can see at the bottom. And this is where we also found the initial velocity of where it would crash into the hole. So that's what I was talking about earlier. And in here, we just plug in all the values that we found into the FG equation, which was the gm m1 over r squared. Here's our GlowScript program. So this is just it running, and you can see in the code that it's moving pretty fast, but one of them shows the velocity. And just for our final results, the orange vector is the net force, purple vector is the perpendicular net force, blue vector is the parallel net force, and listed there's our black hole mass. And in our initial velocity, I already mentioned that in the previous slide. Oh, and the black hole mass is in kilograms. So just what does this mean? So we're asked to see how the net force and the change of momentum is different. So essentially they're the same value, but just calculated differently. So the net force will just use the gravitational formula and just take in the total amount of force. The dp over dt is the change in velocity because that's representing the momentum, which is mass times velocity. And this leads to like representing different themes. So net force is the total amount of force acting on it. dp over dt is the change in momentum. And sorry about the typo, it's a dp over dp. So what if we wanted to enter into an orbit around the black hole? So the new initial velocity that I would need would be smaller than the original initial velocity. And I found this by trial and error, just typing in different types of velocity. And this really makes sense. Why? Because if there's a slower velocity, that means it takes more time to go around, which means that the force will be able to act on it more. And thank you for your time, and have a great rest of your day.